we're going to look at a different type of nucleophilic aromatic substitution that is done using a very strong base. This is the elimination addition mechanism that has a benzyne intermediate. What is done here is you still have an alkyl halide. It's very important that it's an aryl halide. So you've got the halogen on here. And adjacent to it, you need to have one or two hydrogens. You could have them one on one side and none on the other. It doesn't matter, but there are two. Usually we use amide as the base. You do need to have a fairly strong one. Now, I know this isn't the strongest base out there, but it's a fairly strong one. And what it will do is it will remove a proton from one of the adjacent carbon atoms, resulting basically in an elimination mechanism. So this will help you form a triple bond and you kick out a chlorine. It's very similar to an E2 elimination, though it's not exactly the same thing. So as this occurs, we are able to make the benzyne intermediate. This really is a radical, is what it is. I'm going to draw it in a slightly different way here for you in a minute. This is often how I draw it when I think about mechanisms. There's pieces out here. But this is equivalent to drawing a radical species because this isn't a true triple bond. This is what it really looks like because a triple bond has a bond angle of 180 degrees. These bond angles are actually still kind of close to 120. You do have a diradical species. They're not stable, but they kind of hang out together. And these two radicals literally are in sp2 hybrid orbitals. They just kind of hang out together. So it's not really a true triple bond in the sense that you're used to. Oh, I forgot. I got to draw my other electrons on that ring. Sorry, they're there. So your benzyne, it can then react further. It's not stable. And you should have more amide present in the solution, and it will act as an electron pair donor. Now, it doesn't matter which of these two carbons it adds to, but it will add to one of them. And at that point, this pi bond will break and the other electron basically jumps over to the other carbon. So, you get your NH2 group on there, and you've got an anion. Okay. Now the anion can then react with the ammonia that's in the solution and remove a proton from it. And as that occurs, we're able to form our benzene ring again. So first off, we eliminated something and then we added something. So the order of operations is different here, but in the end you are still substituting an NH2 group or a good nucleophile for a halogen. So you're still doing a substitution reaction.